On the program today, lecture, a few words on model fitting version 2, and then the main topic today will be Pam Calculus. Your job this week, among other things, is to take quiz 9. We have now reached the point where the labs are finished and the labs are replaced by the mini project. The mini project has an intermediate deadline on May 11 and 12, where I ask you to do a 10-minute status presentation. 10 minutes is very short. There should be just a few slides, and you should book slots for this presentation. But as usual, you need to be up to date with your quizzes. If you have any questions on your mini project, some of you have pending comments I made, so don't hesitate to speak to me by mail, chat, or any mechanism you would like. Model fitting. We have seen how to fit a distribution in practical cases where we have what we can call a censoring effect, which is what happens when the data that we have observed is limited to some amount, but the distribution that we fit puts a non-negligible weight on the tail, like, for example, a log normal distribution. And we have seen that a correct implementation of maximum likelihood is the right way to obtain good fits. We have also seen last week that there are distributions that have power law in the tail. I'm showing here one distribution that's an empirical one that is related to a web system generator, artificial generator. We find that it has a power law tail, but of course it's not exactly a Pareto distribution. If it would be a straight line in the CCDF in log-log scale, like I'm showing here, we would simply fit a Pareto distribution. But we find lots of very large data sets that have this in the tail only, and then the body of the distribution has something that is noticeably different. Those are probably stable distributions because we know they come from aggregation of many things that are heavy-tailed. But fitting a stable distribution is something very complicated, so we don't even venture doing it. Instead, the practice is to do what we call a combination. A combination occurs when, for example, we say for the up to some threshold A that remains to be determined, we fit a certain distribution, and after the threshold A, another one here. That's a special case of mixing combination distributions that is given by a formula that is given here. If I call F1 the PDF and capital F1 the CDF of the first part, F2 for the second, that corresponds to something like this. So it's a weighted sum, where Q is a number between 0 and 1, of this here, which is a rescaled version of the PDF. This is rescaled such that the integral of this between 0 and A gives, sorry, it's a typo here, it's F1 of A on the denominator. I'm sorry for that. Let me fix it. Here we are. So that's a rescaling factor. The PDF is F1. And if we restrict it to be between 0 and A, of course, the integral will give F1 of A. So I divide by this to obtain a PDF. Similarly, here I have a PDF for the region above A. So I have to rescale by 1 minus F2 of A. And then I weight the two with some weights Q and 1 minus Q here. When we're doing this, of course, with the correct fix, which is here, when we're doing this, what is the interpretation of this mixing of distribution? Here I'm proposing two algorithms that propose an output that comes from this distribution. Now, of course, this weighted combination of those two elements gives a PDF because I've put weights Q and 1 minus Q, where Q is between 0 and 1. So that, of course, is a PDF. I do the integral of this from 0 to infinity. I have Q for the first part from 0 to A. From A to infinity, I have 1 minus Q because that sums to 1. So that is indeed a PDF. here I'm proposing two algorithms which are at the same time interpretation of the random variables that we're simulating if we take this PDF. Which one do you believe is the correct one? I close the poll in a few seconds. Closing. And the majority says both, which is indeed correct. So if we have this PDF, and if we look at algorithm A, what is B, let's say first, what is B producing? Well, B produces first a sample, call it X, of the PDF that is given here. That is what we call rejection sampling. We have seen that rejection sampling produces a sample of the PDF given by a normalizing constant times the PDF here. So it either produces X, it produces X and Y, and with probability Q, it picks either X or Y. Therefore, the PDF corresponds to, given that Q is that the first outcome is chosen, we obtain this PDF. Given that the second outcome is chosen, we obtain this second PDF. And therefore, the overall PDF is the weighted sum by the law of total probabilities, Q times this plus 1 minus Q times that. So B is a correct implementation that at the same time gives us an interpretation of what we do with such a combination. We assume that the data have been produced with some probability from one distribution, subject to the condition that it falls below the threshold, or from the other, subject to the condition that it falls above. Incidentally, algorithm A, let's look at this algorithm. So A draws X until F, which provides exactly this PDF, etc. A does something similar, but first draw U. So it decides whether I should use the first branch or the second. So of course, it produces exactly the same output. With one difference, though, A is probably a bit more efficient in the sense that A calls the random number generator only twice, whereas B calls it 3 times for every, at least 3 times, plus the number of rounds you need to do here, for every output here. So B is more, consumes more random number generator calls and is less efficient, but both are available implementation, are possible implementations. So that tells us what we do when we mix distributions. In fact, distribution mixtures are a topic that is very often used. For example, if you do soft k-means, you're trying, when clustering data, the distribution you take correspond to Gaussian distributions, where you assume the data that I see with probability Q comes from a generator that has generated from one Gaussian distribution or from another one. So that's exactly the same principle here. And like for soft k-means, when we try to estimate, or hard k-means, by the way, when we try to estimate the parameters of the distribution from the data, the classical method of maximum likelihood works perfectly well with some numerical complexity. Here, we are in a very specific case of distribution mixtures, where we can see from the value that we have whether we're in the first case or in the second case. It's not the same thing when we do k-means, for example. But here it's very easy. So that means if I have a value that's below the threshold A, if I know A, I know it must be attributed to a sample from the first distribution. There remains the value of how to set the threshold value here. We'll see that in a second. There remains also the parameter Q to estimate. So in fact, the parameters we need to estimate are, if I recall the formula that we have here, that's the formula. We need to estimate Q and A, those are my combination parameters, plus the parameters of the distribution F1 and F2. In the case of interest here, F1 is log normal distribution, so it has two parameters, sigma and mu, and F2 is Pareto. Pareto in this case that I decide to start at A, so it's a rescale Pareto at A, so it has only one parameter, which is the index, the decay rate that we see on this straight line here. The maximum likelihood estimation can be simplified if we do it in pieces. First, we can observe that the Q hat, the maximum likelihood estimation of Q, is exactly the number of points, the number of data points that fall below the threshold A. Of course, I don't know yet A, so this is a function I call N1 of A, the number of data points such that Xi is less than A. Total number of data points is N, so Q hat is my maximum likelihood estimate. Not surprisingly, we've seen that maximum likelihood tends to provide estimations that are the naive ones. That's exactly what we can see here. Here I'm writing the log likelihood of this big thing. So I'm just writing the PDF. And the PDF is with probability Q given by the first PDF with probability 1 minus Q by the other one. When we take the log, we have log Q and log 1 minus Q that occur. I have a big expression with lots of complicated stuff, but the complicated stuff are the data point, which in this problem are assumed to be known. So my parameter is, for example, here Q. If I want to find what's the maximum of this with respect to Q, I take the derivative with respect to Q, and I find this formula, and it's easy to see that as a function of one variable, it has a maximum when this is equal to that, which gives exactly this formula. Q hat is N1A over N. So the first step. Now, how do we find the threshold? Well, we had such a problem several times in this course when we had breakpoints models. That's models that are very often given in the context, for example, of real-time system modeling, where we want to, in real-time, model what happens. Then we model, we have seen with breakpoints, we have seen that for modeling the congestion collapse in Joe's Wi-Fi shop, for example. So the method here consisted in estimating everything, assuming the breakpoint A is known. So that's a possible way. If I know the breakpoint A, I can estimate F1 and F2, because for estimating F1, then I have simply a formula that we have seen before. That's a censored log normal distribution. We've seen last week how to estimate this. And for F2, we have a Pareto distribution for which we also have a closed form. It's not Pareto here because I've assumed the Pareto distribution starts at A. Now, how do we find A? Well, we can plot the log likelihood as a function, or minus, here the log likelihood, as a function of A, which is what I did here. So I numerically computed the log likelihood. Of course, I discretized. I have a number of steps here. With a few pilot runs, I found the region of interest, or here graphically on the curve, you find that the value of A of interest is in this region that I'm plotting here, somewhere in the middle of this bar here. And I found that there is a maximum, which is not too easy to find, but is somewhere around 138, 139. So that gives me my optimal A. Voila. So doing this, I obtain a distribution that I'm able to fit that gives exactly the red curves that are here. And incidentally, that gives a decay rate and of the Pareto tail, which if the rate is less than 2 will confirm to us whether it is heavy-tailed or not. Voila. This is how in practice heavy-tail is manipulated. In the lecture note, I give more illustration of how this is done in a very interesting load generator called Surge. This one dates a bit. It's old work, but surprisingly, it has not been replaced by anything better, at least with that level of sophistication. It's an example of a benchmark that tries to simulate load that goes to a web server, and it's based on an artificial model where it models the user behavior, where it assumes that the user oscillates between activity period, off period, activity period, etc. That is similar to one of the models we use in queuing theory, the interactive user model. And then you need to do a number of modeling acts, like what is the distribution of all of these periods, what are possibly the number of objects, the distribution of the number of objects. So by taking large measurements, interestingly, you will find that practically all the items that we have seen in this lecture had to be exercised. we find that the active off times are Weibull distribution. They also find Pareto distribution for the number of embedded references, and the distribution of file sizes, that's the one in fact that I've shown in the example before, has a heavy tail and is modeled as a truncated log normal and Pareto. Voilà, for more details, I invite you to go to the paper, to the paper and the summary that's in the lecture note. We come to a conclusion on this model fitting story. So model fitting is very important. We've seen various aspects of model fitting. In this second part, we focused on fitting a distribution, which is one of the key acts that are done in a large number of theoretical studies where you want to simulate or compare algorithms. Then you exercise the load. Remember, from the methodology, having a good model of the load is essential. So good models of loads usually have embedded distributions. In order to choose the distributions, we have to know that they have shapes, and it's important to distinguish parameters that affect the shape and those that do not. We have also mentioned that power laws occur whenever we have very large data sets. They are not anomalies. They are not due to errors in the distributions, and they are typically used by model with Pareto distributions and combinations when we want to model not just the tail, but the complete distribution. Last, we have seen also an interesting but embarrassing result. That's the central limit theorem, which is at the heart of a lot of statistics and explains why we have the Gaussian distribution. Well, it doesn't hold when we have power law with exponent less than 2. In that case, we find different things, and we have seen also the impact on, for example, confidence intervals, or using classical statistics that ignore this fact. Then we see also that this may cause problems. We have seen also how to avoid the problems. One way is to rescale such that the heavy tail will disappear. Voilà. That's all for this module. I see there is a question on the chat. What is the role of Q? I guess this is a question on this model here. So here we model a distribution as a combination here of two distributions, and such a combination, in order to be a PDF, must be weighted by weights that sum to 1. So that's mathematically necessary. And what we have seen is that an empirical way to interpret it is to say, I assume that this data comes from 2 combined generators, one that produces an output here, one that produces an output there, and Q is simply the fraction or the probability of outputs that fall in the first band. Voilà. So without more transition, we move on to the last chapter of this lecture, which is called, with 2 names. The first one is Pam Calculus. That's the name that mathematicians give to it. For statisticians, perhaps we could call it the importance of the viewpoint. Sometimes in statistics, it's called also the problem with ratio games. So we will come back to that immediately. Here's an example. That's an article that there was, you may remember, 1.5 years ago, there was a dispute about Airbnb. So many cities claim that Airbnb is in fact vampirizing the business of hotels and is transforming apartments and houses in general into hidden hotel rooms. And Airbnb said, no, you don't need to make any law about us, because the median occupancy of rented listings, so listing here means an apartment, the median occupancy of apartment is 11%. So you see, our apartments are rented through Airbnb 11% of the time. So that's truly a peer-to-peer system where we take advantage of when people go on vacation, they're happy to have somebody in their house, it makes a bit of money, and then it pays for the vacation. And that is supported by this number, 40 days a year. But then there is a user association called InsideAirbnb.com that had a different statistics that say the median occupancy of the rented listings is 40 to 50%. So there were a large dispute in the press about why is one giving 11% and the other 40 to 50%. And depending on which political agenda you had, if you are paid by the Airbnb lobby, you would go for this one. If you are supporting people who suffer from excessive occupancy in large cities and you're on the political part, perhaps you would be using this paper. Now the question arises, is it simply because statistics is just statistics, people are taking whatever number they want, or is there a more fundamental issue there? And there is a fundamental issue in statistics, which is what we will discuss in this lecture now. Here's another example that's easier to understand. I changed the names to avoid any problem. So in some countries, Sovrail monitors how on time the trains are and finds that there's less than 5% of the trains that are late. But the Consumer Association finds that, according to the consumer survey, 30% of users find that the train is late. So here people are angry because 30%, that means 1 day out of 3, your train is late. So that's a significant event. Whereas here it's 1 day out of 20. So of course that would be a very different experience. Who says the truth here? Well, it's a sampling bias problem. Probably both are saying the truth, or in both cases, it is thinkable that both are perfectly correct, and that the difference in percentages, in probabilities, or in metrics are not due to cheating. This, of course, can happen. There are also statistics that are cheated, but sometimes it's more subtle than that. To understand why, let's see an example that's closer to the problems that we tend to model in this course, so a computer system. And the problem can be related, at least in one instance, to the difference in which we sample to do for a given metric. For example, I can do, if I have a queuing system, like you did in one of the labs, you simulated a queue, I can sample the system with what is called an event clock. An event is, for example, a customer arrival, or an end of service, or anything that of interest that happens in your system. For example, if your queuing system would be coupled with a mobility model, it could be the times at which the random waypoint hits a certain waypoint. So whatever event can be described with a context within the context of a simulation, I can sample the system when an event occurs here. Then if I do that, and if, for example, I'm interested in the average queue size, I will obtain a formula of this kind that says the average queue size is 1 over the total number of events, the size of the queue that I have sampled when there was an event here. So here I put Tn minus 1, it means just before, so that's the queue length, just before an arriving customer. So that's an example that's often used in queuing theory. That is the queue size that is seen by a job that joins the queue. Perhaps that's the queue size of interest. If you are interested in booking, for example, a reservation for vaccination, then what matters is when you decide to try, then you join the queue and how much time do you wait, or which of course could depend very simply on how large the queue is. That's a possible way of defining the statistic. But there's another way of defining the statistic. The other way, which is perhaps more the one of an inspector, consists in instrumenting the code very often and taking the time average. We will see that this is the same as if we have an inspector who comes at random points in time, according to a Poisson process, and samples the system whenever the inspector decides to do it, in a way that's completely independent of the dynamics of the system. That's called the time average viewpoint. So for example, I could ask, what is the average occupancy of the queue? So I instrument my system, I measure every second, for example, what's the queue size, and I divide the integral of what I've seen by the observation period. You did such thing in the labs, for example, in the random waypoint simulation model. I asked you to find what was the average speed as sampled over time, and what is the average speed when we sample the speed at a waypoint. We ask when you take another, you go to another waypoint, you choose a speed, and what is the speed you take? So we look at the time series of speeds and we take the average. Another one is if I ask you every second, what's your speed? I take the average. I have two different viewpoints. I have two different viewpoints, which means I have two different statistics. And in general, you expect them to be different. Here's the gatekeeper example. Gatekeeper is a system that is very frequently deployed in large information systems. For example, if you try to book a vaccination those days in Canton Vaud, you will not go directly to the reservation center. Instead, you will go into a queue that will ask you to wait until the systems is able to serve you. So that's a mechanism that is used in complex information systems to avoid one of the patterns we've seen at the beginning of the course, which is congestion collapse. Congestion collapse is the pattern that makes a system perform very poorly because it spends more resources when the load per load unit when the load is high. Of course, good systems wants to avoid this, and I'm happy to see that the queuing system of vaccination in Canton Vaud is a good system. So we put a gatekeeper. So a gatekeeper is something that will keep all the requests on the side and not devote too much resources to the existing requests here. Here's an example of a gatekeeper that has two processors. One that is fast, so the execution time. One that is, so it's a small arrow, but it's a large number. So it will take a large amount of time. And another one, the green arrow, which is much faster. Why is one slow and the other fast? Well, there can be various reasons. It can be that it's a multi-core machine and one of the processors is busy doing other things. For example, processing the video of a Zoom session or whatever other reasons here. Typically, you don't do Zoom sessions on such servers, but you can easily imagine that the servers are shared with other virtual machines, for example, and that explains the difference in job execution time. Also assume that those different servers are becoming available at the times that are shown here. This is an extremely simple case that is too simple to be true, but roughly speaking, such things do happen. So we see that the red server becomes available they become available periodically, but the red becomes first, then immediately after the green, then you need to wait a longer period, and then the red, then the green, etc. So that's the kind of things that happen when you have servers that have multiple processors, but that are shared also between many virtual machines or many parallel execution tasks, and where you are focusing on one virtual machine, that things like this can happen. This is also your experience, for example, if you imagine the job arrival is you arriving at the railway station in order to go to your preferred location. And then there are two trains per hour that go to your location. One that will come, the red train, that will take a long amount of time, but that will come soon. And another one that will come a bit later here. So the job arrival is, of course, here not completely random. And it is random, but it's not Poisson. We see in particular that there is a pattern between the successive intervals. There's a long interval followed by a small, and also a correlation. After a long interval, you are allocated to a process that takes a long time. So assuming this is the system. Of course, this is not the ideal system. You would prefer a system that is fairer, but fairness comes at a very high cost. And if there is any imbalance in the different virtual machines that are sharing the system, we might see things like that. Now, if I am instrumenting the system for performance, I can do it from two viewpoints. I could do the system designer's viewpoint. This is the one that's very, very often done, because that's the system, that's the way you do it. When you're inside the system, you design it, and then you do things as makes more sense seen from the inside. So from the inside here, of course, as a designer, you will not know exactly what those times are. Those times will change all the time. I'm showing a situation where they are like shown, but at other periods of time, they might be radically different. So here you would say, I will simply observe what are the execution times taken by the different processes, which I can instrument and measure. And I say, I'm allocating two processes or two processors to this task or to this virtual machine. Therefore, one happens to take a long time now, the other less long. So in average, I'm giving to you 3,000. So that's the kind of thing that institutions, systems will tend to give. They give statistics that's based on their view of the usage of their own resources, and then the average wait or execution time for a job will be here 3,000. That's perhaps the story you would get from the system that is renting the resources to you. Now, you could also instrument the system from the viewpoint of the customer by doing spy software, for example, that will send test jobs, which we can also interpret as an inspector that sends test jobs, arrives at a random time. Now, what will happen to such a random job or the inspector? Well, with probability large, which is 90%, you will fall in the first interval and you will be allocated to the red processor. So with probability 90%, your execution time will be 5,000. And with probability 10%, it will be 1,000. So your average execution time that you will measure will be 4,600. So the measured thing by an inspector has nothing to do with the measured quantity measured by the system or the institution that's delivering the resources here. Both are right. Both, nobody's cheating. Of course, they could be cheating, but I'm assuming here they are not cheating. So both are computing with two different viewpoints. And those difference in calculation is called the sampling bias. So perhaps the first thing to know is that this sampling bias exists, which means when there is a metric that is used somewhere in a performance statement, perhaps it's good to ask the question how it is measured. What is the sampling method? And sometimes we might have surprises. Like in this case here, if this guy says, in average, your execution time is 3,000, and you run the system, you have the impression it's more. Well, you do a test, you find something more. Well, it was simply that the measurement methods were different. What we will see is that there are, in fact, methods to reconcile the different viewpoints. This is called Pam Calculus. So Pam Calculus is a set of calculus formulas for relating different viewpoints. So if I find something that is different from yours, I should be able to reconstruct yours by using Pam Calculus. Pam Calculus is sophisticated, but we will start giving an intuitive interpretation here in the form of a heuristic here. Let me explain the heuristic on this example that I just gave here. We want to relate the two averages, the system average and the customer average, and see whether there is a formula that can explain one from the other. The idea of the large time heuristic should sound familiar to you. It simply consists in saying, how would I evaluate these metrics in a simulation? And then by looking at the details, usually we should be able to massage one into the other. So how would I evaluate the waiting time WS seen by the system designer in a simulation? Well, I would simply look, I call X1, X2, X3, X4. This is a 4 here, it's not a typo. I look at all the execution times of all the jobs. And then I take the average over all the jobs. So I've seen n jobs, each of them had a possible execution time xn, that gives me x bar. The customer viewpoint would be a bit different. The customer viewpoint says, if I would arrive at an arbitrary point in time, what would I see? Well, to answer this, I would take the integral of what I call x n plus of t. That's the x I will get if I arrive at time t. N plus of t is the index of the next thing that I will be allocated to. So if I arrive at time 45, then x of n plus of 45 is x1 here, 5,000 here. So I say everybody that arrives between 0 and 90 will have 5,000. So I put 5,000 in the integral during 90 time units. I integrate all of this and I divide by the total simulation time. That's what we obtain when we do a time average here. Now, as I mentioned, at least in simple cases, we can get one from the other. So I have those two formulas that we have seen before. So I break this WC by saying I have to take an integral from the beginning to the end of the simulation. And the integral is of what? Is of a function that jumps only at times t1, t2, etc. So I break the integral between all those intervals. And on one of these intervals, for example, on interval t1 to t2, the x that I choose is x2, because if somebody arrives in this small second interval, it is allocated to the second processor and it will receive a service x2. So the contribution of this integral is here. Now you can see easily that's not a difficult integration exercise. That gives x2 times t2 minus t1, that's this term here. If I sum all those terms here, I find this formula. It's this 1 over t. Now I call S, the interval here, between two consecutive arrows, is the sum of the SI, XI here. Now a bit of standard statistic will tell us that the sum of the SI here, it's 1 over t. If instead I would have 1 over n, so I put n over t in front, 1 over n this, well, it is related to what is called the sample covariance, right? If if it would be zero mean, that's exactly the sample covariance. In general, we have the formula. The covariance of two time series is given by this, the average of the cross product minus the product of the averages. So this sum here is exactly that. And n over t, what is n over t? Well, n over t is the number of arrows I have seen divided by t. So we can call it the intensity. It's the number of arrows we see over time. So it is the number of service opportunities, the number of times a server wakes up per time unit here. This is what my simulation will estimate for lambda. So we obtain this formula. The WC is given to the WS. WS is the system estimate, plus a term here, which is lambda times the covariance of S and X. So we find in particular that if S and X would be independent, so it means if the interval in which you fall is independent of which job execution time you will experience, if those two things are independent, then the covariance is zero, and the two viewpoints are the same. So this is an example of a Pam Calculus formula. It's a formula that relates the two viewpoints and tells us, for example, when the two viewpoints will be the same. It is when there is some independence here. Here I'm giving two sample outputs. So the first one, Sn starts with 90, 10, etc. That's the one that's drawn here in the figure. And the sequence Xn is 5,000, 1,000, etc. And here, the same timings, but the opposite. The red arrow gives a smaller execution time. In which case, do we expect that the customer viewpoint will give a larger statistic than the system viewpoint? I close the poll in a few seconds. And the majority says A, which is the correct answer. Of course, the key thing here is the covariance. So what does covariance mean? Covariance means it is zero when two time series are independent. And it is positive if one time series tends to be in the same direction as the other, and negative in the opposite case. Now let's see here. I have a time series with numbers that are large, small, and the one is large, small. So we see that whenever an S is large, the X also is large. Whenever an X is small, the corresponding X is also small. So there is positive correlation here. So we expect here WC to be larger. The other case is the opposite. We have negative correlation. When S is large, then X is small, so it's negative. In that case, we would expect WC to be less than WS, which means that the customer viewpoint could give less than the system viewpoint here. It's better than the provider tells us it should be. We have a better experience. That could be here because of the negative correlation. When we are in a long interval, we are more likely, which occurs more often, then we find a better processor. So most of the time, we don't have the average of the two, but the better one here. And of course, if they are independent, the correlation will be zero, at least in theory. The sample correlation on a short time series will not be zero, but it will be very small. So the two viewpoints will be compatible here. Well, what I've explained is a pedestrian way, but perhaps the most important one, to find relationship between viewpoints, which is very useful because sometimes we find statistics, as in the two introductory example I gave before, that obviously are based on different measurements. So are we able to reconcile them? Sometimes we need, in order to reconcile them, to find additional statistics. Here we needed to say something about the covariance. But that will allow us to understand whether there is some cheating somewhere, and also perhaps to understand which statistic or which sampling method makes a viewpoint here. Makes much more sense. In general, the large time heuristic is exactly like what I've presented on this example. It consists in formulating each performance matrix as a long run ratio. This is what I call, what would you do if you run a simulation? And then take the formula for one viewpoint and break it into pieces in order to make the other viewpoint. If one, for example, is time and the other is event, then time flows continuously always, and event occurs sporadically. And in that case, you break the time average viewpoint into portions that corresponds to the event. And then if you're lucky and work hard enough, you will be able to compare the two formulations. Important thing is that it's like the little formula. The little formula is an example of Pam Calculus formula. It's a robust method in the sense that all we need is that long runs correspond to averages. So we need that it makes sense to measure things in a simulation, which is what we do most of the time. Any statistic we take is only based on long averages that we take. So it does not require assumptions of the sequence being IID or Gaussian or things of this nature. So it's what we call a very robust set of results. Here's another example where the context is very different, but the methodology is exactly the same. Here I was talking, the classical framework in which Pam Calculus is presented is when we have various timings that are chosen. For example, we discussed measuring what happens to a server at an arbitrary point in time versus at whenever one of the tasks that are able to serve the packets or the jobs wakes up. So at an arbitrary event versus at an arbitrary point in time. But this can be much more general. For example, here we find in the paper that's given here, a SIGCOMM paper of a few years ago, Jennifer Rexford and co-authors measured the file length distributions in two ways. One way is so-called per packet viewpoint, and another one is per file viewpoint. So per file means I measure on I do statistics on a server. I measure all the files that have been transferred. I have a long list of files, of file transfers, and for each of them, they have a given length. That gives me a statistic. And for various types of definitions of the file transfer, or more exactly of the flows, here the flows can be defined as being host to host or subnet to subnet, etc. So we find 4 different curves, but if we take the same curve, for example, the port-to-port flows, we have one curve here or another one. So one of the curves corresponds to what I said. You measure all the flows that you have observed over your time duration, and you do CCDF. We see on the y-axis is the proportion of flows with more than X packets, so that's a CCDF. And here it is in log scale, semi-log scale. It's log scale on the x-axis and natural scale on the y-axis here. But there is another viewpoint that is measured, which is called the per packet viewpoint. So here I'm illustrating this. I have a number of flows, and a flow is made of packets. Of course, I do not necessarily observe the packets one by one or the flows one by one. Typically, all of this is mixed together. But at the end of the measurement, I'm able to say which packet is in which flow. And then I can ask the question, for a packet, what is the size of the flow that you are in? So that gives me a distribution of flow size seen for an arbitrary packet. Right? So I can do the two things. So here, for example, I have 3 flows. So I have a distribution of 3 lengths, and I have 1, 2, 3, 4, 5, 9 packets. I have 9 answers to the question, what is the size of the flow that you're in? So if we do that, of course, not for 9 and 3, but for millions, we find those curves here. Now, we will finish this first hour by asking the question, which curve do you think corresponds to the per packet viewpoint? I close in 1 second. And the majority says B, which is the wrong answer. Think about what happens here. If you ask the packets, in which flow are you? You will have 5 packets. What is the size of the flow that you're in? You will have 5 packets that will answer, I am in a flow of size 5. Here you will have 4 packets who will say, I am in a flow of size 2. So you see that the majority will say, the median will be will be 5. There are more than the majority that says 5. But if you ask the flows, what is your size? You will have 2 flows that say 2 and 1 flow that says 5. So we have only 1/3 of the flow that is 5. That's exactly what we see here. If we look at the median, so we take 50% on the y-axis. For the first case, port-to-port flow, for B, we find a value of perhaps 7 or 8. Whereas for the A curve at the median, we find a value of perhaps 1,000 here. So A must be the viewpoint that corresponds to packets, because if we ask packets, we see more packets in the large flows, so there will be more weight given to the large flows. Well, that's exactly one of the mechanical symptoms that will explain differences in viewpoints. We have just seen that if we sample the flow sizes per packet versus per flow, we obtain 2 different answers. What we will see now is how to relate the distributions of the results of those 2 sampling methods. And for this, I will use the heuristic method that I described just before the break. So the per flow statistic, here I'm assuming I want to obtain not just the mean, let's assume I just want the mean flow size. We will see a formula for the, so the per flow size, I call it SF, and SP, the per flow, the per packet mean flow size. If I have all the data, so here a simulation or a measurement campaign, I call SN the length in packets of the nth flow. So I have capital N flow, and that gives me this average mean, gives me the per flow result. The per packet result, I have capital P packet. I call f of p the size of the flow that packet P belongs to. Oh, sorry, the index of the flow that packet P belongs to. So that's the sum over all packets. Packet P will answer SF of P. That's the size of the flow that packet P is in. 1 over the total size of packets. That's the average that is experienced if you ask all packets or if you sample them randomly. Now, in order to reconcile those throughputs, I do a thought experiment where I put side by side all the packets that are in the same flow. I stress that this is not necessarily how things were measured. Probably this is not the case here for the type of flows that were on the example I gave a minute ago, because those are flows measured on an internet router. But here, as a thought experiment, I put all packets of flow 1 side by side, and I re-evaluate those quantities here. So I write SP. SP is the sum of the answers that all the packets give me. So for flow 1, I will have the answer S1 that comes twice. For flow 2, I have the answer S2 that comes twice, because there are 2 packets in flow 2. And for flow 3, I will have the answer 3 that will come 5 times, etc. In general, we see that the answer S1 comes S1 times, the answer S2, S2 times, etc. So the answer that I have, SP, is 1 over the total number of packets, sum of the square of the flow sizes. Now I compare the two. We just saw this formula. That's the average answer to the per packet question. That's the average answer we obtain to the per flow question. We see that the average flow size is 1 over n, the sum of the n. So it's exactly P over n. The total number of packets is the average flow size multiplied by the number of flows. So if we massage the two together, we obtain this formula here, which can be written using what I call the variance of S from the per flow viewpoint. The variance of S is 1 over n sum of Sn square minus the mean of Sn to the square here, which is given here. So that gives us this formula. The average flow size obtained as a result of sampling packets is equal to the average flow size obtained as a result of sampling flows plus 1 over the average flow size times the variance of the flow sizes here. Again, we find a special case where if all flows have exactly the same size, not a very exciting case, but if that happens, the variance is 0 here, and the two answers will be the same. And the answers that you will get from both viewpoints is the flow size, which is the same for all flows, so there's only one answer, it will be the same. But in all other cases, we found that SP is larger than SF, because the variance is always non-negative. So there is a systematic sampling bias, which, based on the discussion we had at the quiz, is not surprising. There are more packets in large flows. Therefore, the average, when you ask packets, tends to give more importance to the large flows. This quantifies exactly this thing here. We can do the same calculation instead of average by looking at PDFs, and we'll find this formula. The PDF of flow size sample per packet, it's a PDF in discrete time, so FP of S is simply the proportion of packets that gave an answer S to the size that they were pulled. Same, the PDF per flow is the proportion of flows that have a flow size S. Well, we'll find this relationship. The per packet viewpoint is proportional, eta is a proportionality constant, to the product of the PDF per flow multiplied by S. And this is by the arguments that if you ask how many packets have a flow size S, you will have the same answer S times here. So it is not surprising. You can do the same reasoning we said for the averages with a bit more of calculation. You will find exactly this formula here, where eta is a normalizing constant, which means that the two PDFs differ. The FF is in 1 over S, the FP here. Here, for this toy example, this is the PDF of the flow size seen by flows. There are 3 flows. 2 flows are large, 1 is small. The PDF seen by packet, we find 4 and 5 answers here. So we see that the two PDFs are radically different here. So that's exactly the sampling bias. Now let's return to the Airbnb paradox. One instance of one strong pattern that we could not see at the beginning because it's a pattern more sophisticated than just the patterns we saw is exactly this. If you ask, if you sample in a certain way, if you're more likely to find large answers from when the output is large, then you will have exactly the sampling bias we had before. Let's return to the Airbnb paradox discussed in the introduction here. Now, let's give more details how the occupancies are computed. So the occupancy seen by an arbitrary apartment, that's the Airbnb statistic. Let's call it F of S. That's a proportion of apartments that are booked S nights per year. Now, the inside Airbnb.com does a different thing. They ask travelers, they ask members of the, or people interested in this website, whenever they did a booking, to go to the website and give the information, how many how many nights did you spend in this apartment here? So it gives us a different proportion here. Right? So FT of S is a proportion of bookings that occur in an apartment booked S nights a year, right? So FT of S will give the histogram of you spent 2 days in this apartment, someone else spent 1 week, etc. So we count 2 days, 1 week, etc. That's our time series, and the resulting PDF is this FT of S. If we do a similar reasoning as before, do we find any of those formulas here? And if yes, which one? I close the poll in a few seconds. I share the results. Well, the answer is not very clear here, but probably because we don't know exactly how those polls are done, but we're more likely to find something that goes like A, because by the same arguments as we had before with the file durations, we are more likely to ask people who spend more time, we will sample the apartments that were booked many, many times in a year more often. In the extreme case where people would spend exactly 1 night in every apartment, we would find exactly the answer A here, because an apartment that is booked, for example, 40 nights, we would have 40 answers here. So we would find this exactly. To find the exact answer, of course, we would need to find the duration of stays. So we will have perhaps a more complicated formula, but that indicates that this bias is perfectly possible. With a bit more work for this and the other example, you will be able to see in the quiz how to find exactly the the exact ratio between the different viewpoints. So voilà, that's for this introduction, which is relatively non-formal, but I hope I've convinced you that the way we sample data to compute a metric may be important. We've seen the Airbnb, we've seen the train system. You will be able to clarify that exactly in the quiz. And that apparent paradoxes may come from not explicitating the viewpoint here. So that may be intentional. And very often when you have system or institutional statistics, they are like the one we saw for the jobs that are allocated to servers. We will tend to have a viewpoint that's based on the resources and not based on the experience done by customers here. So the trains company will tend to count how many trains are late, whereas the users will tend to count how many users will experience a late train. And those two things typically are different, except sometimes, for example, we've seen when there is independence or zero covariance, then the viewpoints coincide, but most of the time they do not here. So take-home message, sampling method is something as a performance specialist that you have become now, something that you should screen carefully. It's usually not possible to find or not interesting to find exact mapping formulas, but knowing whether the sampling bias will exist or not, like for the file size distribution, is important. What we will do now is how we can facilitate our task by doing what is called Pam Calculus, which is methods that are a bit more formal than what we saw to give systematic changes of viewpoints. And surprisingly, we'll see that it has also an important impact in simulations that we have done, in fact, for example, of the random waypoint. The theory it's called Pam Calculus by the name Pam, which is a Swedish mathematician who was interested in computing statistics for telephone systems. But the theory itself has emerged much later in a family of East German mathematicians who developed it for the analysis of queuing theory. So this has been essentially developed for queuing theory, and we will see a few queuing theory examples. But as I've tried to motivate, it applies to all kinds of situations where the sampling bias might play a role. Pam Calculus is a bit complicated if we want to do it very, very formally. I will try to give a gentle introduction based on simulation here. So the simplest way to think about it is assume we do a simulation, like you know how to do now. You've done quite a few in the labs, which means I have a machine that out of a sequence of calls to the random number generator produces some state at time t. There's the concept of time t. And assume at a time t, I can sample some quantity. I can do, that quantity can be anything. And I will be interested in finding different viewpoints for this quantity that I'm observing. There can be several quantities. Here I'm focusing on one, and this quantity is not necessarily a single real number. It can be any dimensions. Pam Calculus applies to stationary stuff. So stationary is the keyword here. We need a simulation to be in stationary regime. So it does not, the formulas, at least mathematically, are not rigorously true if the simulation does not have a stationary regime. There are a few technical assumptions that I'll skip here. One example that you have seen in the labs is, for example, if I'm simulating a mobility model like the random waypoint, which is perhaps the simplest non-trivial mobility model. So ST is the state of the simulation. So it contains the current position of the mobile at time t, and also the elements of the trip that it is performing. So the speed and the next waypoint. So because by this model, we pick a next destination and we go there according to the straight line. So in this very simple model, we need only where we are, at which speed, and where we are going. More sophisticated mobility model would have more information, like the attracting numbers, like the selected roads that you may use, etc. Now, the Pam Calculus framework applies to a measurement that is jointly stationary with the simulation state. So jointly stationary, That means that it does not change if we change the time origin. Remember, the simulation is stationary. So if I observe the simulation 10 years later, theoretically, assuming it can survive 10 years, then I should see statistically no difference. And then if I shift time by 10 years, the X that I would see 10 years ago is the same as the X I would see now, or the same algorithm would produce the same X here. So it is depending on the simulation state in a deterministic way, on a way that is invariant by shift of time origin. It depends not just on the stationary test, it may depend on the complete history and future of the simulation, but in a way that's invariant by shift of time origin. I'll give one example and one counterexample. For example, for the random waypoint simulation model, if I'm interested in the current speed at time t, and the time to, so that's a function of the current state, that is jointly stationary. If I ask, if I'm interested in the time to be run until the next waypoint, that is something that I can calculate now, so it depends only on the current state, that is also jointly stationary. Obviously, if I change the time origin, if I do the same simulation, but I said that I reset time to 0 just now, then those values of xt will not change. The index t will change, but the value that comes as a result of polling the system will not change. Now, of course, something that would not be jointly stationary is if I ask what is the absolute time, what is the timestamp at which the last waypoint occurred, and if I change the time origin, the answer will change, of course. If I reset time exactly when I ask the question, the answer will be negative, it will be in the past. If I don't, it will be positive. So this is not jointly stationary. So that's a very mild assumption. The thing that is not mild is that we assume that the simulation has a stationary regime and has reached the stationary regime. Why do we do that? Well, it is to make sense. This is how mathematicians make sense of what they call an arbitrary point in time. That seems very simple. And in data sciences, we tend to use that thing all the time. We say, this is a thing sampled at an arbitrary point in time, or sampled at an arbitrary location, or sampled at an arbitrary anything. So to sample at an arbitrary anything, we need to put a distribution on the thing. The problem is we cannot put a distribution on time. Other than we can of course put distribution of time, but we cannot put a distribution of time that is time invariant, that is uniform, which is what we would like. If I have a time interval between 0 and 10, I can take a uniform distribution between 0 and 10. I mean, any time between 0 and 10 is as likely to occur as any other time. And we know this distribution. This is the uniform distribution between 0 and 10 with PDF 1 over 10 for t between 0 and 10 and 0 outside. So if time is bounded, a uniform time makes sense or can be defined. If time is unbounded, it cannot be defined. So we cannot, because with the normalizing constants would be infinite here. So this is this paradox in the theory of probability, is that an arbitrary point in time, arbitrary means we are in a stationary regime for the simulation. Any time instant is as good as any other one, but we cannot represent this by a process of choosing a time instant by drawing it from a distribution. It's not possible. So one way to go around that is mathematicians say, well, we assume the distribution is stationary, and since it is stationary, if xt is jointly stationary with the simulation, the expectation of x of t does not depend on time, because if I shift time, I will have the same output. So since it doesn't depend on time, this is how we call, that's the result of a sampling done at an arbitrary point in time. That's the theoretical interpretation. There's another more physical interpretation, which we will see next week, which has to do with the so-called pasta property. It can be seen that this mathematical formulation is also exactly the sampling we would get if we sample the system according to a Poisson process. In fact, I said it's not possible to sample the time uniformly at random, but it is possible to sample a process of time points uniformly using a Poisson process. Except if you do that, you will need to say what is the rate. So for example, if I say in average, I sample every second, so I have one observation every second, then I can have a Poisson process with rate lambda equal 1 that is well defined. Of course, it will be random. I do not know exactly at which points in time I will sample the system, but I know that I will have in average 1 second between two samplings, and the distribution between two consecutive sampling times will be exponentially distributed with mean 1 second here. So if we do that, which is in fact the only mathematical way in which we can sample time uniformly, then we obtain exactly the same viewpoint here. Not surprising. For a formal discussion, we'll see that next week. We need some notation to make sense of the formulas we will see. And the notation is given here. So I assume I have a simulation here, and I observe the simulation at specific times of interest, which I call selected transitions. So selected transitions is when specific events occur that I can define by looking only at the simulation state changes. So formally, I can define a subset in the cross product of the simulation states, which is well defined, at least if the state space is finite. And then this subset here, which does not include the diagonal, it includes no points in the diagonal, is said an event if at some point the state just after t and just before t happens to be exactly in this selected set of pairs of states here. For example, if I have a queuing system, I may be interested in arrivals. So the arrivals corresponds to combinations of two states where in the second state there is one more customer than in the previous one. So in that case, F0 will be all the pairs of states such that in the second state there is one more customer than in the first one. That corresponds to arrivals. So in general, we can, for any simulation, we can define specific events in this abstract way. Now, because the simulation is assumed to have a stationary regime, this sequence of time events here is also stationary, and it's called a point process. A point process on the set of real numbers. So that corresponds to specific points in time where something occurs. Another example we have seen is for the random waypoint mobility model is when the mobile reaches its end of trip. Remember that in the random waypoint model, the mobile picks a destination, goes there. Then when it has reached its destination, picks another one and goes there. So we can look at the instance at which a mobile reaches the next trip, and it was the next destination it had chosen. So as you can see, that can be very general. It can be anything. It can be the time at which something specific occurs in a simulation, the time at which a customer arrives, the time at which a waypoint is reached, etc. Now, in terms of notation, when in the context of the Pam Calculus formula, we will always use this convention, since the sequence of time events here is infinite. In this theoretical model, things are stationary, have lasted forever, and will last forever. Of course, this is just a model. Then we call T0 the event that is the last one before 0. So we assume always that T0 is less than or equal to 0, and T1 is the first after 0. And in this context, since things are stationary, 0, like any point in time, corresponds to any arbitrary point in time. So very often the formulas will use t equals 0 as the arbitrary point in time. So that's the difficulty of this framework, is just to understand this thing that I'm presenting now, which seems a bit weird, but it's less weird if we think that the simulation is stationary, and then we have a sequence of time instants that are anywhere, and I choose the label based on their values, as opposed to, like we usually do, T0 is my first value, T1 the second, etc. Here we have to think a bit differently. In this framework, the Pam expectation is defined as follows. The Pam expectation of some quantity, xt, remember xt is something that I'm interested in measuring. For example, the time at which the speed that you have now. I can ask a mobile, you're a mobile in this random waypoint mobility model. You've run it for long enough, it's stationary. I ask you, what's your speed? I do that at time t, I obtain an answer, xt. Now assume I don't do that at an arbitrary point in time, just like this, but I select only points in time in which something special occurs. For example, I do that when you're in the middle of your trip, or just at the end, or at the beginning. For example, here, I do that just at the end of a trip here. So I ask you, what is your speed, given that we are at one time, one of those special times here? That is what is called a Pam expectation. So you see, it's a conditional expectation. It's the expectation of some quantity, given that a certain point process has a point at has occurred at exactly this time. So when we say the Pam expectation, there is something understood. It is with respect to a given point process here. And because everything is assumed to be stationary, if I ask the mobile at time t, what is your x, I will have the answer, which is the same as if I have, or we said the same distribution, so the average, the expectation will be the same. If I ask at time 0, so E0 of x0 will be ET of xt. So normally, this is what is truly called the Pam expectation. The Pam expectation, which is written often with a little 0 in superscript of the expectation, means exactly this. So expectation under Pam of something is the average of something sampled at time 0, given that time 0 is precisely a point of the stationary point process, which is also the same as the average of something, given that we sample at an arbitrary event time Tn. So that looks very complicated, and we need this formalism to be able to do nice and easy to use formulas. But the take-home message is the most important one. The Pam expectation of something that is measured from a stationary process or a stationary simulation is the average of what we obtain, average in the general sense. So something may be any question we ask, for example, what is the quantile? So the average of something sampled at an arbitrary event time Tn here. So that corresponds to the event viewpoint here. So let's illustrate this for the random waypoint. The random waypoint is shown here. Voilà, we have a little. So if I ask, what is your speed? The expectation of the speed at time 0 or at time t, which should be the same if the simulation is stationary, we can view it as the average speed observed at an arbitrary point in time. And the Pam expectation is the average speed, if we take the point process of trip ends, is the average speed observed at a trip end. The speed observed at a trip end, well, this is the speed that is selected by the construction that you did in the lab. When I arrive at a trip end, I select a speed by applying some rule. I draw some I generate some random variables, and it gives me the speed. If I take this sampling method, I obtain what is called the Pam viewpoint. If I take the time stationary viewpoint, I obtain another one. What you've done in the lab is to empirically, numerically find results for the distributions of the speeds, for example, at an arbitrary point in time versus the arbitrary speed chosen at an arbitrary point in time here. I spoke of conditional distribution. Well, strictly speaking, this is true only in discrete time, which is not very nice. In practice, we always reason in continuous time, but I'll do an exception here because otherwise the math becomes unnecessarily sophisticated. In discrete time, it's very simple. What does it mean? Taking the Pam expectation given that an event occurs at time t. Well, if we're in discrete time, I can put a sequence of zeros and ones saying at every time t, if an event of interest occurs, end of trip or customer arrival, I say n of t is 1, as otherwise n of t is 0. Then we have the conditional expectation of y given that at time t, n of t is equal to 1. So this is well defined by the formulas of probabilities. As long as n of t equal 1 has a non-zero probability, which hopefully is the case, otherwise there will never be any arrival here. So if I apply the simple formulas of probability 101, expectation of y given nt equal 1 is given by the expectation of the product divided by expectation of n of t. Remember, n of t is a binary variable, so this is just the probability that nt equal 1. So this is exactly this simple formula. So if we're in discrete time, Pam calculus is simply, again, an exercise on conditional probabilities. So we can view what I said about the importance of the viewpoint as, again, when we take conditional things, conditional probabilities, of course, we change the probability. In continuous time, unfortunately, this doesn't work. For example, if I take a Poisson process, which is a continuous time point process, if I say n of t is 1 if there is an arrival exactly at 1, well, I can define this. But the probability that a given t has n of t equal 1 will be equal to 0. In continuous time, the probability that an arrival occurs at exactly one time that you specify is 0. Of course, you could say, but there's a contradiction, because if I sum all the probabilities, I should find 1, because I should find at least some positive number. But we have here, if time is continuous, well, this sum becomes an integral, and we have lots of nasty things, so it doesn't work as nicely, as naively as I presented here. So for that, you use what is called a Radon-Nikodym derivative. So limiting cases, you can imagine this as you take a time slot that is finite, you let it go to 0, and in the limit, you will obtain the Pam calculus here, the Pam probability. I define Pam expectation. I use the word Pam probability. In fact, the two are related. If I know how to compute an expectation of anything, I know how to define a probability, because the probability of an event is the expectation of the indicator function of this event. So the probability that x0 belongs to w, for example, given the Pam probability, is a probability that x of 0 is in w, given that some transition occurs at 0. So it's the same conditional things, but for probability. In particular, we find this thing that we should remember. The Pam probability that t0 is 0 equal 1. Why? Well, because of this convention, because of this convention I gave here, we say t0 by definition is the last negative or 0 value of of time events. Under the Pam probability, we say we condition on the fact that at time 0 there is something. So it's like in forecasting, we condition. That means we assume we know for sure that at time 0 there was an event. So if there is an event at time 0, then t0 is equal to 0. Which means, again, this thing here. t0 is equal to 0 always under the Pam probability. So I gave a perhaps heavy formulation. We saw the large time heuristic. The large time heuristic consists in saying I compute averages by doing a long simulation run, and for time averages, I divide by the total time. Here I'm assuming time is discrete, otherwise it would be an integral. And event averages, I do something similar. For event averages, I sample the system. I look the system only at time tn, and then the expectation I obtain is the 1 over n, the average of what I have observed those time tn's. So this is perhaps something that's easier to understand, more difficult to work with, but that's the intuitive explanation, at least that I have, of Pam expectation versus standard expectation. The standard expectation of a stationary quantity, you obtain it by taking the time average and dividing by the total time of the simulation. The Pam expectation of the same quantity is obtained by sampling the quantity at times of interest, Tn, and taking 1 over n, the results, the average of what you found here. So Pam probability of something is probability that something happens at an arbitrary event, whereas the stationary probability of something is the probability that something happens at an arbitrary time t, which should be independent of the time t if the simulation is stationary, and it should be independent of which particular event index n we're considering if the simulation is stationary. This framework allows us to introduce a general concept called the intensity of a point process, which we have seen always in simulations. If I have a simulation where I look at particular events that I call Tn, for example, arrivals, lambda is the average number of arrivals per time unit. That's exactly the intensity. So in a simulation where I see n events and the total simulation has lasted in total Tn, of course, if I increase n, I might change Tn, then lambda in the simulation will be estimated as n over Tn here. Well, for any stationary point process, if the point process is stationary, that means the expected number of events I will see over an interval of duration 1 time unit, for example, is the same over all intervals of length 1. So, and this quantity, which is the same, is called lambda, is the expected number of events per time unit. We have seen our good old friend, the Poisson process. The Poisson process is a process where events occur at that time Tn, such that the difference between two event arrivals is ID exponential with rate lambda. And of course, it has this particular property of being memoryless. But given that you saw an arrival now, that gives you no clue when the next arrival will be, because the exponential random variable is memoryless. It has this interesting property of the tail that we have seen, is very specific and might be useful to know whether we should use this distribution or not. Well, if we apply the definition of intensity, then we can see easily also that the lambda is exactly the same. So the rate of this exponential distribution, by the way, that's why it's called a rate, is exactly the average number of points of the Poisson process we will see over an interval of duration 1 time unit. In fact, for the Poisson process, it is known that the distribution of the number of points, the number of arrivals we see over an interval of duration t, has a Poisson distribution with parameter lambda t, has a mean lambda t, and the distribution itself is known is a Poisson distribution. Perhaps this is why it's called the Poisson process here. So for the Poisson process, that's easy. For our simulation of the random waypoints, well, we can ask the question, we can be interested in the process Tn, which is when the mobiles reach waypoints here. Well, it's probably not a Poisson process. You've seen that in the lab, at least empirically. And here the intensity will be simply saying how many times per time unit the mobile will reach a waypoint. So how much this quantity will be depends on the parameters that we've seen. Since the mobile is choosing a point uniformly in the area and chooses a speed also, well, if the area is very large, then the mobile takes a long time to get to the end of its current trip. So if the area is very large, the intensity will be small. If the speed that is chosen is also very large, then the mobile will get quickly to the next point and the intensity will be larger. So unlike the Poisson process, the random waypoint model is an example where the parameter lambda is not directly one of the inputs of the simulator. It is something that we can calculate from the parameters, but it is something that is derived from the simulator. We will see, in fact, how to calculate it. And this is our first Pam Calculus formula, which is given here in gray. The intensity, or the inverse of it, is exactly equal to this Pam expectation of T1 minus T0, which is also the Pam expectation of T1. So what does that mean exactly? Well, remember that T0 is always less than 0, and T1 is always strictly larger than 0. So when we do the Pam expectation, we assume that T0 is equal to 0, so this is why those two are the same. Well, this is just the Pam calculus way of expressing something simpler. This something simpler says, well, this is the time I sample when I sample 2 consecutive events. So I take an arbitrary transition that I call transition 0, and I look at the time until the next transition, which gives me T1. And I say, how much time does it last? So the intensity is 1 over the mean time between events. So if I want to calculate how many points I have in average in a simulation, how many events I have in average in a simulation, what I can do is I can simulate what is all the times between events, and the average of that will give me 1 over this point here. So this is one formula that is fairly obvious in a simulation. Now the trick is that it is true for any stationary process within the framework that I give. So if I have a stationary process, I'm interested in special events that are derived from the stationary process, then the intensity, the rate at which such events occur, is 1 over the average time between two successive events. If we come back to the Poisson process, we know that the distribution of time between arrivals is exponentially distributed. We know that the mean of an exponential distribution is 1 over lambda. Therefore, lambda is exactly the intensity here. So, which is the formula I gave before, then it follows from this Pam Calculus in formula, which is called the intensity formula. For the random waypoint, well, it means what I need to calculate is the average trip duration. So the trip duration is given by how long the trip is and at which speed it is taken. So I would need to calculate this, and that will give me the intensity of the random waypoint. So let's conclude with this little question. At a bus stop, we find that the distribution of the time between two consecutive buses is given by a uniform distribution spread between 15 and 25 minutes here. Which of the following statements are correct here? I close the poll in a few seconds. And Dirac on this answer 3 buses per hour, which is of course the correct answer. The intensity formula says to us it's 1 over the average time. The average of this distribution is 20 minutes. In hours, that's 1/3, so that gives 3 per hour. Very simple, but, and this is my true conclusion, what are the small characters? Under which conditions is the formula valid here? I close the poll in a few seconds. Closing, closed. And the correct answer is stationary. And that is the remarkable thing. So of course, a Poisson process is stationary, so it applies to a Poisson process. If we have a process where the inter-arrival times is an ID sequence, then it will also be stationary. Therefore, this will apply. So it applies to all the 3 cases, but we don't require those specific assumptions. We only require stationarity here. So even if there are correlations and lots of things, this will be true. So that's a remarkable feature of the Pam Calculus results. And one way to understand it is, again, to think about if I would estimate this in a simulation, then I would simply have those games of comparing an average to the other, which are completely independent of distributional assumptions. Voila, that's the end of the lecture for today. That's the end of the lecture. So thank you very much and take care. Enjoy the mini project and don't hesitate to speak to us for any question you have. So we stay online as usual for the sessions on Tuesday and Wednesday for any questions on your mini project. So some of you asked me questions, so I will invite some of you in a breakout room in a few more minutes. In the meantime, I wish you a good week. Take care.